In the known universe, if you don't learn to adapt, you get left in the dust.
Come on, baby. No, you can do it.
We're transforming our earthbound technology to take on the rigors of the cosmos.
So let's see if a bullet will fire in outer space.
Each new creation propels us faster, clears a new path.
3, 2, 1.
And pushes us to the edge.
Here we go! Holy cow!
Get an up-close look at our transforming technology. Because in space, extreme takes on a whole new meaning.
You're in my house now.
The stakes are high because we're about to break down our most well-known technologies and see how they must be transformed to work in space.
Space is a completely different environment than the environment on Earth. There's a vacuum in space, and there are different temperatures in space. So the question is, what sort of modifications do we need to make?
Some technologies could have unlimited potential, while others might fail spectacularly. To see how much space changes our technology, our first stop is your driveway. Would your car make it on the moon? Or Mars? NASA doesn't think so. So they have transformed the technology of your favorite automobile and created an entirely new type of vehicle. And mechanical engineer and astronaut Mike Massimino is about to kick its tires.
Here we have the state-of-the-art in astronaut transportation. This is a SEV, which means Space Exploration Vehicle. It can take a 45-degree incline going up. It can turn about itself. It can go over a rock about 2 feet high. So you can go just about anywhere with this thing. So let's take a look inside. Here we go. Okay, to control this thing, I have this control stick, which allows me to control it in any degree of freedom. I also have a video display, so we got cameras everywhere. Control panel allows me to select the gear, the speed, to control the whole vehicle right here with this. So we've got all kinds of video capability here. Allows me to see on the side. I can see out the back with a camera that's mounted on the back. There's also cameras on the wheels in case a wheel gets stuck. If you come across something that you see is interesting, you can pull the vehicle right up to it and then get a closer look through this bubble. It's a nice capability. Not only is this a vehicle, but it's also a place that you can live for a while. If you're out on overnight on an excursion, the back of the chair folds into a bed. So you can sleep and live on this thing for a couple days if need be. You don't have to worry about gasoline because it runs on battery power, and the batteries are charged by solar energy. Coming around the back end, these two doors allow you to dock the spacesuit so you can open the door from inside, jump into the back of your spacesuit, and then go off on doing your spacewalk. And this is a big advantage over our current system that takes hours to prepare. Here it's just a matter of minutes.
But why do our vehicles have to transform into this futuristic giant? At Johnson Space Center in Houston, Texas, astronomer Andy Howell is about to find out. He's getting behind the wheel of a standard SUV to test if it could hold up on an extraterrestrial surface. Only thing is, he'll be racing Mike and the rover. Off-roading is about to go out of this world.
Now the course we got here, we're going to start over on flat ground, and then we're going to go through some mud. But that's when the similarities with Earth start to depart. Behind me, what you see is our moon terrain. So we're going to go to the right of the moon terrain, and then we're going to take on the craters. A big one and then a smaller one. If we survive the moon, we're going to try to make it up Martian Hill here, which has lots of rocks and holes. And whoever makes it to the top of the hill, we declared the winner.
My biggest advantage is speed. Even if I get stuck, I should still have plenty of time to get up here.
So there are times when you're exploring space that you want to go really fast. And I got a feeling this is one of those times where slow and steady is going to win the race.
The hardest part is those craters. I'm really worried about getting stuck. That's a lot of gravel.
I think the toughest part for the rover is going to be getting around Andy after he gets stuck. And I hope his insurance is paid up because we might have to just go over him. We'll see you on the top of the hill. Good luck. Get ready to eat my moon dust.
You might be fast in your space shuttle, Mike, but that thing goes like, what, 9 miles an hour? This is gonna be easy.
We're not going on a highway. We're going on a planet. You're in my house now.
Three, 2, 1.
Going down, Massimino.
Well, he made it through the mud. So far, so good for Andy. Let's see how he does on the moon.
I see you in my rearview mirror, Massimino.
All right, he's going down a big crater.
Hill. Baby, now you can do it.
The loose, crushed gravel makes it incredibly difficult for the SUV to get any traction.
Ooh, come on, crater.
Having the power of 12 wheels and weighing twice what the SUV does, the SEV has no trouble with traction in the craters at all.
He is still in there.
Oh! This thing is not made for craters. Come on, baby, come on. I know you can do it. Yeah. All right.
All right, Andy's clear. We'll get through this one now.
Now, let's see if we can get this hill.
But this hill is made of sand and rocks.
Oh.
And with the steep incline, Andy's SUV can't get any momentum.
Oh, the thing's gaining. Curse you, Massimino!
There we go.
Mike's SEV, on the other hand, can easily climb a slippery 40-degree slope.
I don't think we need to worry about Andy catching us on the way up here.
And roll right over rocks.
Just turn around. We're going to do a pirouette here. Oh, look. There's Andy. Let's go see how he's doing. Hey, what happened? You need a tow? How about a push?
Damn it.
Doesn't look like he's doing so good.
Man.
Be careful, there's rocks.
No kidding. Congratulations, Mike. I guess you really are the king of the hill.
Well, it's not me. It's the space exploration vehicle. You did the best you could, Andy.
What can I say? I'm not a race car driver. They don't train me for this stuff.
If Andy thought his SUV took a beating on the mock lunar surface, on the real one, things would get a whole lot worse. Without the benefit of Earth's atmosphere, any SUV's combustion engine won't even start unless it's sealed up and pumped full of oxygen. Even if it gets running, this set of wheels will find it hard to get traction on the loose lunar soil, which blankets almost the entire surface. And the spinning tires kick up an even bigger problem: harsh lunar dust, which is like powdered glass. These small fragments can penetrate most seals and will quickly gum up the hydraulics and transmission. Even if we overcame all these problems, in the low lunar gravity, this big 4x4 will go flying the second it hits one big bump.
You would catch a lot of air on the moon. Wear your seatbelt. It's crazy up there.
Moving around on solid surfaces like moons or even other planets is one thing. But flying through space is going to require an even greater level of transformation. The first big problem? Propulsion. Here on Earth, we take to the air with jet engines.
A jet engine uses a combustion process. So basically sucks the air in, increases the pressure, and then they ignite that air with propellant in the engine. And then the air gets actually pushed out the back, which pushes the airplane forward.
But what flies on Earth isn't going to fly in space.
A jet engine wouldn't work in space because there's no air in space. There's nothing to contract and then explode out the back. So a rocket is used. And a rocket engine has all of the material contained inside of it. So all the burning can happen right there. And by shooting stuff out the back, it propels the rocket forward.
So what do we have on Earth that can transform into a rocket for space? The answer's a bit surprising. A gun. That's right. You can take the same process that fires a bullet and convert it into fuel tanks and a combustion chamber. And then your loaded gun becomes a loaded rocket that's off to the races. It might seem far-fetched that a gun and a rocket could be the same. So the only way to see if it's true is to perform a little experiment. Trying to fire a gun in space. Scientist Steve Jacobs has it all set up. And aerospace engineer Sigrid Close and Andy Howell are eager to see if it'll work.
There's an old question, will a gun fire in outer space?
Yes.
You're pretty sure?
I've seen it in movies. They don't
you've
lie.
seen it in movies.
They don't
Movies
lie.
never lie. Okay,
Yeah.
Sigrid, do you agree with his analysis?
I'm not sure. There's a combustion process going on within the gun.
Well, yeah.
So we need air. There's no air in space. There's no air in here.
No air in You're thinking like a scientist. This is great. We're just going to find out. Let's load the gun, then we'll turn on the vacuum pump, removing the air, and then I'll push the magic button. So let's see if a bullet will fire in outer space. There's a bullet. I'm going to put it in the cylinder. Got it? Ready to go. Okay, that looks pretty good. So we sealed up the tank. It's airtight. I'm going to use this pump to remove that air. Oh boy, it's going down fast now. Okay, I'm going to turn off the vacuum and prepare to shoot this thing. You folks ready?
Ready.
All right, here we go. Countdown. 3, 2, 1.
To transform our ordinary earthbound machines into tremendous out-of-this-world technologies, we need to know if an everyday gun will fire in space. Andy thinks so. Sigrid isn't so sure. So Steve has put one in the box, drained out all the air, and is about to pull the trigger.
You folks ready?
Ready.
All right, here we go. 3, 2, 1.
It did fire.
What do you see, Andy?
Oh, nice little hole.
Nice little hole there.
It worked. Didn't sound like much though.
And that is because?
Sound doesn't travel in a vacuum.
That's right. That's
And
right.
it was kind of quiet.
It was kind of quiet, kind of muffled. So Andy, what have you got to say about this now that you've seen it?
Well, I actually knew that gunpowder has its own oxidizer.
So this makes perfect sense. We took all of the oxygen out of this chamber, but we didn't take all the oxygen out of the gunpowder.
Right.
How is there oxygen still inside the gun? The answer is that it's secured within the bullets. When a gun's hammer strikes a bullet, it ignites the gunpowder inside, which is a mixture of charcoal, sulfur, and a substance called saltpeter. Saltpeter is rich in oxygen, and the oxygen chemically reacts with the other elements to create the explosion that fires the bullet. And this allows a gun to fire easily in a vacuum. Pulling the trigger might be similar to a rocket powering through space, but we've got other problems, like the need for an even bigger transformation: steering. Our Earthbound aircraft maneuvers are also highly dependent on air. And Mike Massimino and pilot Greg Johnson are about to take to the skies to see why.
All right, Greg, you're gonna get a chance to fly today.
It's gonna be great.
But why don't we go over a little bit about how the control surfaces work?
Well, let me talk about the wing. You got these little ailerons, and these what make us turn left and right. If you take the stick and move it to the right, this aileron on the left side goes down, the one on the right goes up, and the airplane rolls to the right. And in fact, if you take this stick and we roll it quickly to the right, you're gonna go around and do an aileron roll 360 degrees in 1 second.
We're gonna try that later.
The horizontal stabilizer moves with the stick also. And as you move the stick, this moves to pitch the nose up or down. And in fact, if you pull really, really hard, we can pull 7 Gs.
That's not a G's for us.
So let's not do that.
No, we won't do that today.
And the final surface is right up there, that little rudder. You can use the rudder to keep the nose to go left or right, but in general, we want that thing straight so we can go really, really fast.
Yeah, we want to go fast, and we want to have fun.
Time to see how these controls steer an aircraft at speeds over 800 miles per hour.
Ready for action.
Ready for action. Here we go.
That's 908, center Roger, climb and maintain level 230.
Right, level 230 for that's 908.
Accelerate just a little bit here, and we'll try one aileron roll.
Moving the control stick to the right pushes the left aileron down and right aileron up, rolling the jet to the right.
All right. And now we're pulling back on the stick.
By doing this, Greg moves the horizontal stabilizers, causing the nose of the jet to pitch up further into the sky.
And we're kind of doing this big roll. Now we're upside down. And we should come right back to the same heading and the same altitude that we started. And it looks like we got it. All right, heading home. Flying a T-38 jet gives us an opportunity to be in an environment working with another crew member to fly the airplane. And it gets us ready to work together and fly in space.
Though we've got no problems flying in our own atmosphere, if we take an aircraft like this into space, our familiar way of navigation goes berserk. Just like a T-38, when a 747 flies, it uses ailerons on the wings for roll, horizontal elevators for pitch, and a vertical rudder for the yaw. It's all good until the jet reaches space, and then everything goes south. With no air to pass over these control surfaces, our jet spins out of control. And that's the last thing we want to happen in space.
The reason why space can be an issue is because, let's say you push on some object. That object's going to keep going and going. Here on Earth, we have things like gravity pulling it down to stop it. There's nothing like that out in space. This is why when we see astronauts doing spacewalks, for the most part, they're usually tethered. It's because any action that they do, they could potentially spin out of control.
And spinning out of control is exactly what Mike Massimino is about to do. The only difference is, he's going to try and master this problem with a little help from Steve Jacobs.
This thing behind me is called Orbitron. We're going to try to use this contraption to prove how things react in space. We're going to get motion going in one direction and show that there's no way it's going to stop unless we give an opposite reaction to it.
Are you ready to go, bud?
Ready to go.
Good for you.
Jake.
You climb in there and I'll help you a little bit.
You want to come with me?
Sure. Let's see if we can get two in that seat.
Good.
Fine. Now we're really going to clamp you in.
Yeah.
I'll loosen this thing
important.
up. Right there we go.
That feels good. Yeah.
Right there. Okay. Feel snug as a bug in an Orbitron?
So how's this thing going to work?
Well, you've got two thrust handles, right? And they're connected to compressed gas behind you. We've got two nozzles. Look over there to the left. You'll see.
I see that one right here.
Yeah.
That's going to spin me toward you.
There you go. Let's start her up. I'm going to start her up. Okay. And the one on the right.
It's going to spin me away from you. There's a nozzle right there.
There you go. So you'll be able to correct action and reaction.
All right.
So here's what we're going to do. We're going to get you spinning in several planes of rotation and see if you can apply the appropriate amount of reaction to stop some of that motion. So you ready to do it?
Yeah, let's go.
We'll see if we can recreate some space here.
Okay, let's light the candle.
Let's light the candle. Yeah, go ahead. Hey, here it goes. Here we go. Holy cow. Oh, my goodness.
Houston, do we have a problem?
How you going?
Or will Mike be able to use the blasts of air to right himself?
Come on, Mike. Come on, Mike. Hey, you're doing it. You're doing it. Look at you. You should be an astronaut, man.
You think? All right, so I think we successfully demonstrated Newton's laws. What do you think, Jake?
Oh, I think you did a great job.
And I didn't throw up.
And you didn't throw up.
How's that?
You did good.
All right, thanks, man.
I'm impressed.
That was fun.
How does this test show the transformation needed to make an aircraft fly in space? Bursts of gas like these will turn out to be our ace in the hole. With no atmosphere to control the roll, pitch, and yaw of our passenger jet, it looks hopelessly doomed. But if we transform it into a space shuttle and give it a reaction control system, we're back in business. The RCS thrusters allow the shuttle to change direction with small coordinated puffs of compressed gas. And now our spacecraft can precisely maneuver so well, it can dock perfectly with the International Space Station. Flying away from our atmosphere to the vacuum of space may be problematic. But sometimes we don't need to change our technology. We just need to make it supersized. That's exactly what's possible with many kids' favorite playthings, magnets.
If we didn't have magnets, what would we put on our refrigerators? But really, they serve a lot more uses in everyday life. Speakers have magnets. You use magnets to read a credit card. Motors have magnets. I mean, that's one of the most important uses of magnets.
But there's different types of magnets. The permanent ones used on your refrigerator, and also electromagnets.
A permanent magnet is always on. It's a property of the material. You got a magnetic field that's always there. An electromagnet will only work when there's a current running through it. So it's a temporary magnet that you only get induced by an electric field.
But what if you could turn an electromagnet into a machine so powerful it could launch projectiles that would leave almost every jet aircraft in the dust? Well, the Navy isn't imagining it. they've already made it. And this magnetic transformer is called a railgun. Here at the Naval Surface Warfare Center in Virginia, the Navy is testing its latest version. And the Chief of Naval Research, Rear Admiral Nevin Carr, is eager to see this futuristic artillery get some action.
Behind me you see the Navy's laboratory railgun. It's actually a launcher. This weapon can fundamentally change the way we do long-range strike. With a large weapon like this that can deliver a payload over a long, long range at very high rates of speed, you can fire more of them, and you can do so more precisely.
What we're standing next to is the pulse power system for railgun. Each one of these modules is 3 megajoules of pulse power. There's about 100 megajoules in the entire facility. About half of what a house would draw in a day. And it doesn't sound like a lot of power, but we're going to dump all of that in 10 milliseconds. That means in 10 milliseconds, that bullet goes from a standing start to Mach 7.5. So after we've charged the capacitors, we dump that charge into the gun. This is the breech end. This is where the bullet would go in. So you would load the bullet in this fashion. The current would go in through the bottom rail, come through this armature, come back, and that's going to push this bullet down bore. So through this bulkhead is the muzzle end of the gun. It actually provides the best view of the rails themselves. You can see copper rails top and bottom. They're separated by insulators. When the bullet comes out, it'll exit in front of these panels and it'll head downrange. So the bullet's coming out of the gun at 2,500 meters per second. That's about 5,500 miles per hour. If you could maintain that speed, it would go from Virginia to Los Angeles in under 45 minutes.
Here's how the massive magnetic gun does all this. The 5 million amps are sent into parallel copper rails. Once they're conducted, the electricity produces powerful magnetic fields around each of them. One positively charged, the other negatively charged. To get this connection, you put an armature between them. The resulting magnetic fields push it down the rails, releasing a projectile at incredible speeds. Now it's time to see what this bad boy can do from the safety of the control room.
This is the control room. We are separate from the railgun building. The entire railgun is all controlled from this room right here.
Ready to charge.
Charging.
Once it reaches its maximum voltage, we'll have a 3, 2, 1, and a fire.
A projectile is about to take a long journey down an outdoor test range.
Is the deck ready?
System is ready.
We're ready.
All right, 2 bells. Video.
2 back.
Range instrumentation.
2 back.
Data acquisition.
2 back.
Pulse power.
2 back.
Firing director.
Ready.
Turning on control power.
Stand by.
Enabling. 3, 2, 1.
At the Naval Surface Warfare Center in Virginia, the U.S. Navy is getting ready to test one of the most powerful technologies on Earth. A gun that's transformed the power of magnets to launch projectiles almost 8 times the speed of sound.
3, 2, 1. Fire.
A high-speed camera captures the sheer force and power of a projectile as it accelerates out of the gun muzzle, superheating the air behind it and screaming down the range. It's traveling close to Mach 8, more than 5,000 miles an hour, to a target miles away. One thing is certain. You don't want to be on the receiving end.
Go ahead and confirm.
1 kV.
Man, of course, has always been trying to harness the power of the universe. This is just a different way.
But we could use the same magnetic power of a railgun in an even bigger way. transforming it into a spacecraft propulsion system called a mass driver. Using long metal rails with electricity running through them, we could create a supercharged miles-long runway. We could put this device on the moon, and without any atmosphere or substantial gravity holding us back, this mass driver could launch us to other planets and beyond. But magnetic Big Bangs require an awful lot of energy each time they fire. We need to transform technology that's more focused, more efficient, and more versatile.
Initiating sequence.
When it comes to these features, nothing beats a laser.
LASER stands for light amplification by stimulated emission of radiation. The idea is that you put energy into a special material, and that material emits light. And by bouncing that light back and forth, you build up an intense beam of a single color of light.
Here on Earth, we use lasers in CD and DVD players, at the supermarket, and even in surgery. If you want to see the laser that's inside your DVD player transform into something out of a sci-fi movie, a group called Cobham Analytic Solutions has just what you're looking for. They've created a life-saving laser so powerful it's used to destroy roadside bombs in war zones. And theoretical physicist David Kaplan is at one of their hangars in Huntsville, Alabama to see it fired up.
This is Zeus. Zeus is a high-powered infrared laser mounted on top of this Humvee. This laser puts out 2.5 kilowatts of power. That's 2,500 watts. Now imagine a 100-watt light bulb multiplied 25 times. What a laser can do is it takes all of that energy from all 25 bulbs and focuses it into a very narrow beam. That transfers an enormous amount of heat to a very small spot. First thing we're going to do is we're going to take this steel plate, set it up, and burn holes through it.
Initiating sequence. Firing tag laser in 3, 2, 1. Firing tag. Moving to initial point. Fire negation laser.
Wow, it's bright. Wow, that didn't take long. Why does it explode out like that?
Well, what happens is, as it's just about ready to punch through, what you're seeing is the last little bit of metal being exploded out the back.
That's cool.
We're putting about 2,500 watts in a very small area, about 3 millimeters. So it's an enormous amount of power in a really small spot.
Take a look. The whole point of that was to show that you could transfer heat over a long distance and get it to this metal and blow very carefully spaced holes here in this metal plate. Next, we're going to take our tightly focused beam and put it through some organic material, namely this hot dog. So let's see if we get a hole or some other effect.
Ready for hot dog engagement. Fire negation laser.
That's happening. Ooh, it's smoking. Okay, whoa! I don't know what's in a hot dog, it burns like that. And it's still going. Seems like a hot dog is a lot more powerful than a sheet of metal, yet it's gone.
Hot dog destroyed.
That hot dog's dead. Look at that.
Even the skewer is dead.
Mm-hmm. The laser blasted it. The heat was transferred, but it took a while to get through it, though. Why is that?
In the metal plate, there's no moisture. Melted right through the metal. Now, the hot dog, we had to boil it a little bit before we got through it.
So a lot of that energy was just boiling the water, just heating the material, and eventually got us through it.
That's correct.
What we're going to do is an experiment where we defocus the laser. That's going to spread the heat around all over the surface of the hot dog. It's going to be the same amount of energy, but because it's spread over a larger surface area, it shouldn't destroy the hot dog. And hopefully, it'll be tasty.
Lasers are armed. Firing on the hot dog target. Fire negation laser.
I think that's steam, coming out of it. I think that's the water in the hot dog evaporating. Hey, that looks good.
Oh, man. Good enough to eat.
That's a key, defocusing, huh?
All right.
That's pretty good. Well, I guess that's the key. You defocus the beam, you distribute the heat nice and evenly. I mean, that's a lot of wattage for a single hot dog, so maybe this is not the most efficient way. But we see the same laser with the same amount of energy, you can get completely different results.
Lasers may be precise and powerful in the controlled environment of a hangar, but Zeus isn't meant to punch through steel. It's got a bigger mission: saving lives. Time to head outdoors and see if this laser can bring the heat.
This is Redstone Arsenal.
This is where we blow things up?
Yeah, it's a laser-approved place where we can actually put ordnance items out and blow them up. It's pretty cool.
And does stuff go flying everywhere when we blow
these? It goes zinging by.
Have you been hit before?
Yeah, a couple times. Taking a fragment into the really thick armored glass in the front.
But we'll be okay?
Oh yeah, we'll be safe.
Okay.
We'll be just fine.
Our first example of what we're going to shoot today is called a BLU-97. It's a submunition. They're primarily used for anti-vehicle and anti-personnel by the military.
So when you shoot it with the laser, are you just trying to trigger it so that it explodes?
Oh, no. We're using heat. So what we want to do is just hit it with the laser on the outside of the device, and then that heat will transfer in and will couple with the explosive filter material, and you'll cause a detonation.
Heat it weakens the material on the outside, it burns the inside, and then it just breaks open.
Yep,
essentially.
exactly.
Are these the biggest explosives you work with?
Oh, absolutely not. This is a 155 artillery round. It's about 87 pounds, and our laser is quite effective at that. We can do that at a very large range away from the device, so that makes it very safe.
So why don't you use a sniper to shoot these from far away? Why do you need a high-powered laser?
Well, you could do that, but you need precision accuracy, and Zeus allows us to be 300 meters away in the safety of an armored vehicle, and we've got just pinpoint accuracy. I could hit any key on your cell phone at 150 meters, so I can very precisely aim at this device.
So let's go shoot them.
Yes, that sounds great. Let's do it.
It's this accuracy over long distances that could make lasers the ideal technology to transform for deep space use. But we have to make sure they work on Earth first.
Yeah.
Well, how do what do I do?
Well, have you played a video game before?
Well, sure, yeah.
All right, well, we've got a video game controller. Basically, you just use this to point and aim. So go ahead and give that a whirl, yeah.
Okay.
And then you have two triggers. Here's the tag laser trigger, that's the green one. And then you have the negation laser pointer. And you'll turn that on first, and then you'll see the green dot show up, and you'll move that dot onto the target.
Okay.
And then wherever that dot is, when you pull the trigger on the high power laser, you know, we'll start blowing things up.
Cool. I'm ready.
Go ahead and arm.
Okay, I'm arming.
Okay, you are now armed. Pull the trigger on the left.
The tag.
Yep, pull that. Now, move the beam director until you get that on the target.
All right.
Okay, that's good right there. It's a pretty good spot. Fire when you're ready. Pull the right trigger.
C6 negation.
I feel nervous. I don't know.
Are you ready?
I'm ready.
You're pumped. You're ready to go.
I'm ready.
Let's do it.
Okay.
Pull the trigger.
Whoa.
Oh, right. You did it, man.
You filming that? It didn't explode immediately. It just heated the thing up. But it only took a couple seconds for it to heat enough for the munitions inside to explode. And I didn't realize, because I was looking at the screen, but this whole field over here caught fire.
Zeus made short work of the small munition. To see the full extent of what it can do, we're gonna need a bigger bomb.
3, 2, 1.
Firing. Arming.
Searching for the biggest tech transformations in the known universe has put David Kaplan behind the controls of one of the mightiest lasers around.
Oh, right.
He's at the Redstone Test Center in Alabama with a military-grade laser called Zeus. It's used to save lives by destroying mines and bombs in war zones. And David gets to put this science into action by targeting a highly explosive artillery shell.
All personnel are cleared.
Coming down.
Mitigation laser going high. 3, 2, 1.
Firing. It's like it's sparking. Whoa! Holy crap. A laser is not something that immediately moves, shoots in and explodes the device. What a laser is doing is just transferring heat to it. It's heating the metal, it's heating the entire object until eventually it's so hot that it explodes the device. It was very nice to be very far away from this object because we can see the hole it has created. Anybody anywhere close to the thing would have been destroyed. Damn.
Lasers may be a valuable anti-mine device on the modern battlefield. But we can take all this power and transform it for use in space. The idea is to use a laser from a remote location to power spacecraft propulsion.
In movies, you see lasers disintegrating objects. But a laser could potentially propel things into space. If you have a spaceship and you have a material at the back, the laser hitting that material will cause ablative heating. That means layers of the material will be ejected off of it just from being hot and will propel the spacecraft forward.
That's right. A laser could be transformed into a type of interplanetary gas station. As a ship heads towards the outer planets, it absorbs a laser beam, using it to burn onboard fuel. This beam would be so precise and strong, it could originate almost 1 billion miles away from a platform orbiting Earth and still push us to the farthest reaches of the solar system. But of all the technologies we can transform, one literally blows all the rest away. Nuclear power.
Some people imagine using nuclear weapons or nuclear energy to get a spacecraft into space. That explosion could potentially be used to propel a spacecraft at extremely high velocities.
This idea first originated in the mid-1950s with a project called Orion, and it even had a working NASA design. The plan was to take all the power of a nuclear explosion and transport it to space, transforming a destructive device into a galactic power source. If one of these nuclear packages was placed behind the spacecraft, when it exploded, the spacecraft would ride an incredible shockwave, eventually reaching speeds that would let us travel through the galaxy in record time.
Of course, you have to get the nuclear weapon into space through our atmosphere, and if any accident occurs along the way, you could kill millions of people. So watch out for that kind of thing. Think about what you're doing.
These types of concerns eventually shut down the project. But today, as nuclear weapons are being decommissioned, if we can make this type of power safer, it could open up the rest of the cosmos.
You can think of a nuclear weapon as a very bad thing. Using nuclear power in positive ways is a way we can transform something destructive into something that can be a huge advantage in getting us long distances more quickly.
Space travel is really hard. We're not built with rockets built in. We got to use our brains to figure this stuff out.
As we go further and further out into the universe and stay in space for longer periods of time, we do need to transform our technology. We're going to need to transform our vehicles. We're going to need to transform a way to generate power.
We're really going to have to commit a lot of resources to do it right. But if we do it I have full confidence that we can go wherever we want.